we're going to be reviewing complex numbers. Recall that I squared is defined to be -1. So another way of thinking about that is that I is the number, the imaginary unit, that is equal to the square root of -1. Now that allows us to be able to simplify expressions like this. The square root of -25, because we know that that's the square root of -1 times 25, which makes it the square root of -1 times the square root of 25. And then we can simplify each of those individually. So we get 5 from the square root of 25, and we get I from the square root of -1. And we can simplify an expression that looks like this, the square root of -20, in much the same way. Often I would just take care of that negative first and just write it as I square root of 20, and then think about simplifying that radical in the regular way. So since 20 is 4 times 5, out would come a 2, and we'd have 2I square root of 5 as our simplified version of this particular expression. So complex numbers are numbers that actually are defined to look like this. A complex number is a number is a number that can be written in the form a plus bi, where a is an element of the reals and b is also an element of the reals. So for example, 4 minus 11i is a complex number. So is square root of 19 plus 1.8i. It's a complex number. If it can be written in this form, it's a complex number. Even 14 is a complex number, because although it doesn't look like this now, the only requirement is that it could be written that way. And of course it could be written as 14 plus 0i. And if you're thinking, well, 14 is a real number, that's right. Real numbers are subsets. The set of real numbers is a subset of the set of complex numbers. So let's just write that. To remind you that a real number, any real number, is also a complex number. And how about a number like this? 9i. That too is a complex number, although it doesn't look like this, because it could be written in the form 0 plus 9i. If the a part is equal to 0, sometimes we call that pure imaginary. So that would be a pure imaginary number. But what I want to get to is how we do perform operations with our complex numbers. So let's move to that now. And we'll start with addition. When we're adding complex numbers, it's actually quite straightforward. We add the real parts together, and we add the imaginary parts together. So our real parts are the 9 and the -3. And on this one, we don't even need to take a step to distribute the ones. We could just add those real parts together. So we have 19 and -3. That's 16. 16i plus 11i is 17i. And it's as straightforward as that. If we're subtracting complex numbers, we do need to make sure that we distribute that negative. So it would be 3 minus 25i minus 4 plus 6i. But again, we combine the real parts and we combine the imaginary parts, and we have our complex number written. Remember, when you're writing a complex number, we usually write it in this order. in the form a plus bi with the real part first and the imaginary part second. Let's move on to multiplication. Multiplying complex numbers feels a lot like multiplying binomials together. It feels a lot like FOILing them out. We do that same process. So we multiply the real part, the 3 and the 7 together, and the 3 times the negative 6i, and the 2i times 7, and the 2i times negative 6i. And now we keep in mind that I squared is equal to negative 1. So this is really 21 minus 18i plus 14i minus 12 times negative 1. Right? Anytime we see an I squared, we could replace it with negative 1. So to simplify, we have 21. This becomes a plus 12. Let's just add those together. 21 plus 12 is 33. And we have negative 18i plus 14i is minus 4i. And our multiplication is finished. We also have the idea of conjugates when we're talking about complex numbers. Notice if a plus bi is a complex number, then z bar or z conjugate is a minus bi, and these are called complex conjugates. So let me remind you what happens when we multiply a number by its conjugate. So in this case, we would have 1 minus 4i times its conjugate, which would be 1 plus 4i. And we multiply much as we did in the previous example. 1 times 1, 1 times 4i, negative 4i times 1, negative 4i times positive 4i. And as you recall, when you multiply conjugates together, those middle terms drop off. So we end with 1 minus 16i squared. But again, I squared is equal to negative 1. So we have 1 plus 16, or 17. So notice we multiplied two non-real numbers together, and the product was real. If you multiply complex conjugates together, your result will always be real, and that ends up being important. A couple of examples from now. Let's move to finding the quotient of two complex numbers, and we'll start with one that looks like this. Write this quotient in standard form. Standard form for a complex number is in a plus bi form. So we don't want any I in the denominator. For a problem like this, we can take care of that I in the denominator very simply by multiplying by I over I. For me, this feels a lot like rationalizing denominators when you're working with irrational numbers. So in the numerator, we're going to distribute the I. So we'd have 13i minus 25i squared. And in the denominator, we have just I squared. If we simplify, that means we have 13i. Now let's see, this is negative 25 times negative 1, so why don't I just write that as plus 25 over negative 1. So we have 13i over negative 1 and 25 over negative 1. We're going to do that division and write the real number first, or the real part first. So 25 divided by negative 1 is negative 25. 13i divided by negative 1 is negative 13i. And we have just written this number in standard form. Let's do one more. We're going to write this quotient in standard form as well. Notice now we have a complex number where a does not equal 0. So we need a number that we could multiply by 4 minus I so that we won't end up with an I in the denominator. In other words, we want to multiply 4 minus I by a number that would give us a real number. And here's where the idea of conjugates comes into play. We want to multiply this by the conjugate of the denominator. So we have 2 plus 7I over 4 minus I. And I do mean that we're going to multiply both the numerator and the denominator by the conjugate of the denominator, so that we won't actually change the value of the fraction. We multiply by 4 plus I over 4 plus I in numerator and denominator. If we do that, in the numerator we have 8 plus 2I plus 28I plus 7I squared. In the denominator, we have 16 plus 4I minus 4I minus I squared. In the numerator, we have 8 minus 7, right? That 7 times I squared would be a negative 7. We can combine those. 8 minus 7 is 1. And we have 2I plus 28I, that's 30I. In the denominator, our 4I and negative 4I will cancel. And now we have 16 minus what will become negative 1. So that's 16 plus 1, or 17. And often, for emphasis, we separate these terms over the 17. So the A and the B really stand out. So we would write this as 1/17 plus 30/17 I. So you can really see this in A plus BI form.